Hey, welcome back. Today we're going to review chain rule and implicit derivatives. This is something we've talked about before in the past. So before we get started on what the directions here are telling us, we're going to go ahead and just kind of get started. So let's say we have this function. This is x squared minus y cubed x plus sine xz minus 1 equals 0. And what we're asked to find is the partial of z with respect to x. So if I want to find the derivative of this is my implicit derivative. We're going to use implicits here. And in order to find that derivative, we are going to use our implicits. So let's take a look at x. Well, if I'm taking the derivative of x, remember only y, x, and z are my variables. We are saying again, y is constant, so anything with a y in it is going to become 0 when you take the derivative. So when I take the derivative with respect to x, we would just get 2x. Now remember, there's really a dx here, but that just becomes 1, so we don't really worry about that. And we would get minus, over here, we're taking the derivative with respect to x. This just becomes y cubed. Again, dx, but again, we don't worry about the dx, it's just 1. And then we go over here, plus. Now we got the sine of xz. So this is our chain rule right here. So we do have a chain rule at this point. So we take the derivative of the outside, which becomes cosine of xz. And then multiply by the derivative of the inside. Now be careful, we're taking the derivative of z with respect to x. So we do the first times the derivative of z with respect to x plus the second z times the derivative of x, which is just 1. And of course that minus 1 becomes 0, and this just equals 0 right here. And what we're going to do is we now then have to solve for this dz dx. Now that's the old way we would do it back in calculus. And it was a very lengthy way, plenty of room for error right there. Matter of fact, this is my 4th time doing the video and my 1st time trying to get that one right. So in another video that we talked about earlier, we said there was a shortcut to do implicit derivatives. And what they want us to do, and this is what this says, to differentiate an equation implicitly with multiple variables, we're just going to set the equation equal to a function. So if I set our implicit equation here equal to this f of x, y, z, if I make this equal to a function, all we had to do was find the partials, and then we can use, there is a rule for quotients for this, and we're going to talk about that in a second. So if we set the derivatives, so if we set the function, the equation equal to a function of x, y, and z, we can use our chain rule. When we use our chain rule, we would get the following. We would get the partial of f with respect to x multiplied by the derivative of the inside. Now remember, we're finding the derivative with respect to x here. So all these have to be with respect to x. So we would get the partial of f with respect to x. There's my outside derivative. Multiply that by the partial of x with respect to x, which is my inside. But again, that just becomes 1. We talked about that right up here. Next, we would take the partial of f with respect to y, and then the partial of y with respect to x. Now, we don't have to worry about this one because, again, we're saying y is a constant. So this whole term just becomes 0. And lastly, we would take the partial of f with respect to z, and then the derivative of z with respect to x. And this is what we want. So in other words, what we're going to be left with is just the partial of f with respect to x times, plus the partial of f with respect to z times the partial of z with respect to x equal to 0. And I can solve for this, because that's what we want to find. So since we know, again, like the partial of y with respect to x is 0, the partial of x with respect to x is 1, and if I were to solve for a partial of z with respect to x, we would just get the partial of f over x, the partial of f over z, and the partial of f. These would just cancel out. And what you're left with is the partial with respect to x divided by the partial with respect to z. Remember, all this right here in notation-wise, right? Because the partial of f with respect to x, that's just fx, and then this is just fz down there. So this is our rule. So we came up with our rule the other day that says if I want to find the partial of x of z, if we want to find the partial of z with respect to x, we take the opposite. We change our sign because from solving, I'm going to have to subtract. We get negative fx over fz, the partial of x over the partial of z. And that is our rule. And if we take a look over here, if we look at our function right here, let's take a look. This is the exact same problem. So this is an example. If we want to find the partial of f with respect, the partial z with respect to x, we take the derivative with respect to x, which we get 2x minus y cubed plus, this is chain rule, we will get the cosine of xz times the derivative of the inside with respect to x, which is z. And then we take the derivative with respect to z. Well, those are just 0, 0, because they're constants here. And we would get the cosine of xz times the derivative of xe with respect to z. We get the x on the outside. And so my rule just says take the partial of with respect to x and put that over the partial with respect to z. And this is our answer right there. All right, so let's take a look at a quick example. Let's take a look at an example here. So we have this implicit function, x squared y squared minus 4xy plus 8xy. Whoops, sorry. Minus 4xy plus 8x equal to 0. And we're asked to find the partial of y with respect to x, dy dx. Well, our rule says to get dy, to get dy dx, our new rule says I'm just going to take the partial of x, divide that by the partial of y, and I make it negative. So we're going to go ahead and find those. Well, we're going to find first the partial of x, which is just 2x. I don't worry about the y squared, that just becomes 0. This becomes then minus 4y plus 8. And there's our partial. If I find the partial of x, or partial of y, we get 2y minus 4x, and there's our partial there. Now remember, this does have to be equal to a function, so since it's equal to 0, it's really easy. I can just say, scratch out the 0, make that x, f of xy, right there. It's only different if it's not equal to 0, then we have to do some algebra to move it around. All right, so therefore now, to get our final derivative, we're going to take the partial of x, which is this 2x minus 4y plus 8, divide that by the 2y minus 4x. Don't forget the negative, okay? Remember, where that negative comes from is when we do the algebra, when we're solving here, when we're solving algebraically. If I'm solving for the partial of z with respect to x, we have to subtract the partial with respect to x. And that's where that comes from right there, so don't forget about that. All right, so let's try another one here. For number 2, we want to find the partial of y with respect to x and the partial of x with respect to z. So I am going to need, for the partial of y, dy dx, I am going to need the partial of f of x and the partial with respect to y. For dx dz, my rule says I'm going to need the partial with respect to z and divide that by the partial with respect to x. Now, I typically just put my negatives on the top one just so I don't forget about them. So we're going to need all of the partials here. So the partial with respect to x, this just becomes 2x. Again, the y is a constant, that just becomes 0. even the 4zy, that just becomes 0 because I'm only looking at the x's. And over here, we're going to get plus 4xy. Now again, this does have to be equal to a function, so I just scratch out that 0, make it f of xy. Set that equal to a function. Fy, just for your information, we're going to get 2y. This becomes minus 4z, and we get plus 2x squared. And the last one, the function with the derivative with respect to z, 0, 0, we get minus 4y, and I think that's it. And I can just plug these in. The partial, I get negative, the partial with respect to x, I'm going to use parentheses here, 2x plus 4xy, divide that by the partial with respect to y, 2y minus 4z plus 2x squared. And then the partial, dx, this should be a dz there. There we go. So the negative of the partial with respect to z over the partial with respect to x. And you can simplify that, make it 4y over 2x plus 4xy. And again, you can even divide out by 2 if you feel like it. Very easy to do. All right. Now the last one's a little bit trickier, because if you notice, with the last one here, oh no, it's not equal to xy. So this we need to make it equal to xy, f of xy. So this one we have to do a little bit of algebra, so we got to bring our x over. So we would get the function f of xy would equal tangent x minus y minus the tangent of y plus x minus x minus x. And just leave it at that. You can say it equal to 0 if you want to. You don't have to do this part. Okay, this is just good. So we want to find dy dx, which is going to be the negative partial with respect to x over the partial with respect to y. And we want to find the partial dx dz, which is going to be the negative partial with respect to z over the partial with respect to x. Whoops, I messed up here. Let me see here. This, oh no, that should have been a z right there. Sorry about that. So you have y plus z, I just copied it wrong. No problem there, easy to fix. Alright, so the first thing we're going to do is we're going to find the partial with respect to x. Alright, so, oh no, we got to take the derivative of tangent. Okay, that is, what's that? Anybody remember? That's right. Secant squared of x minus y, and then minus 1. The partial with respect to y, this is going to become secant squared x minus y. Be careful, the chain rule says I got to multiply this by a negative 1. I can't spell tangent either, that should be tangent. And this is going to become minus secant squared y plus z, and that's just going to become times 1, so we can just leave it right here if you want. And then let's see here. Then we got to take the partial with respect to z, and this is just going to become negative secant squared y plus z, and again, so it's going to be times 1. Right there. Alright, now there's a couple things you can do here. You can leave all of this alone, and that's fine. You can leave all of that alone. I mean, or you can use some trig if you get bored to say, you know what, Mr. Warnow, I know my trig values. This is just equal to tangent squared of x minus y, and you can write it like that as well if you want to use your trig identities. You don't have to. Alright, so over here we get negative fx, so we get negative secant squared x minus y minus 1 over the partial with respect to y. Bring my negative out to the front. We get negative secant squared x minus y minus secant, oh, ran out of room, secant squared y plus z, and there is your derivative. And then to get the derivative dx dz, we take the negative, the partial with respect to z, so that becomes positive secant squared y plus z over the partial with respect to x. And again, you can write it as the tangent if you want to, or you can write it as the secant if you want, in the secant form if you want to. Doesn't matter, I'm going to use the secant squared because that's what we already have at the beginning. Minus 1. Right there. Alright, so I hope you guys enjoyed the video, and we'll see you all later. Bye-bye.